Okay, good morning, Calculus 1. We're moving into Chapter 3, although this stuff in Section 3.1 is included on the Chapter 2 test, okay? It still involves limits, but it is a brand new big idea, although I think we've alluded to it, and it's this idea. In pre-calculus, you can always get the slope of a line. Everybody knows how to do that. The change in y over the change in x. It's a ratio. Change in y over change in x. In calculus, we can find the slope of a curve. But the concept is to get the slope of a curve at any point, what we do is we draw the tangent line at that point. So if I wanted the slope at that point, it's the slope of that line, which is tangent to the curve at that point. If I wanted the slope of the curve at that point, I mean, it's a curve. So it doesn't really have a slope, but it does when we say it's the slope of the tangent line to the curve at that point. So at that point, there's a tangent line that touches the curve in one point only. You know, by the way, it could touch somewhere else, but at that area, or at that point, in that vicinity, it just touches at one point. And we find the slope of the tangent line. So cool, that's the concept. How do you get the slope of a curve? You find the slope of the tangent line to the curve. Now the problem with that is it's called the tangent line problem. The tangent line problem is that you only have one point. And we're used to subtracting the y's, subtracting the x's to get the slope between 2 points. So the solution to that problem is this. The solution to that problem is the derivative. The derivative of a function is the slope of the tangent line, and it's this. Here it is. And you've seen this before in Chapter 2, so this, in a way, this is not new. What's new is me calling it the derivative and making a big deal out of it. And this is a big deal in calculus. We do this for the rest of calculus. We do derivatives. At some point, we do some anti-derivatives, but Chapter 5. But anyway, the derivative of a function is the slope of the tangent line. So that's our goal, is to find the slope of that tangent line, which is the slope of the curve, essentially. So those were some little general pictures. Here's a specific picture. And so I'll try to illustrate this. Like I said, we've done this before. It still involves limits. The derivative of a function is called f prime of x. We use a little prime symbol here. So that's not the function. It's the derivative of the function. And what is it? It's the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. We've seen this in Chapter 2. We've worked with it, and maybe we even knew what was going on. I've tried to explain before. You're finding the slope, but this delta x is going towards 0. So it was the slope between 2 points, but it's sort of converging to be the slope at one point as delta x goes to 0. And that's called the derivative of the function. And so we can execute that. Let me just try to illustrate it for you here. So if I have a point x on this function, there's the x value. If I plug x into the function, I'm looking for the slope of the tangent line. If I plug x into the function, the y value here is f of x. Okay? X and y. X and y. If I move over to a new x, I'm going to add this delta x. That's a little change in x. I'll add that and I'll get to this new x called x plus delta x. When I plug x plus delta x into the function, I get another y value called f of x plus delta x. You guys with me? Plug an x into the function, there's the y value. Plug that other x into the function, there's the y value. To get the slope between those 2 points, we would do f of x plus delta x, that y minus that y, because you know to do slope, you do the change in y over the change in x. The change in, I could do that x minus that x. If I do that x minus that x, the x's cancel. I'm left with the change in x, so I get the change in x. So that's the slope of the black line. That's the slope of what they call the secant line. It's sort of a it's kind of an average rate of change on the function. But if I want the instantaneous rate of change, now I just changed my language a little bit there, but the slope of the tangent line is the rate of change at that particular instant, then I do this. I put the limit as delta x goes to 0. And it's cool, there's probably some nice animation videos where you watch that happen. If you watch delta x go to 0, you can watch this point move in here. As this point moves in here, they call this a secant line, by the way. This secant line gets closer and closer to what would become the tangent line, the green tangent line that touches at one point. As delta x approaches 0, this point moves in and you get the slope of the tangent line. To me, it's very obvious. I think I explained that pretty well. So that's this formula, and you should memorize it. You should learn how to use it. It's called the derivative. Like I said, it's the slope of the tangent line. You know, in general, we use the word slope, but a slope is a rate of change between two variables. So when we're kind of just talking abstract y and x, we call it a slope, you know, but if y is the population and t is the time in years, it's the rate of change of the population. If y is a distance and t and x is time, then that's a velocity. We learned that, I think, a little bit earlier in chapter 2. So a velocity is a rate of change. It's the speed. Slope is synonymous kind of with rate of change. The slope between 2 points is an average rate of change. The slope at a single point is an instantaneous rate of change. It's the rate of change at a particular instant, which is the derivative, the slope of the tangent line. So, slope of the tangent line, I'm going to use that phrase here for you. Instantaneous rate of change. Instantaneous rate of change. That's another term for the derivative, or use of the derivative. Like I said, it could be the velocity at a particular moment, not some average velocity between 2 points. That's cool too, but it would be an instantaneous. It would be the velocity at a particular moment. Instantaneous velocity. You know, the notation for the derivative is you have a function, and then you do this process, this limit process, and you get what's called the derivative. And what is the derivative? It's a new function. It's a new function, and it's the slope of the tangent line. So it's a new formula that tells you the slope of the tangent line. But we denote it like this. Now, if the original function is called y, then sometimes we might use y prime for the derivative. So, you know, the original function is f of x, or maybe y. Here's another notation. Sometimes we take the derivative of y with respect to x. That's how we read that. It's just another notation that means the same thing. You know, when I took the limit of this as delta x goes to 0, I called it, that numerator is the change in y over the change in x. You could think of it like this, as delta x goes to 0. And what happens is when you get a very small change in y, we call it dy. A very small change in x, we call it dx. So as delta x goes to 0, this quantity becomes this quantity. It's called the derivative. It's still called the derivative. Here's another one. They do the derivative of the function y with respect to x. I don't hardly ever use that one. I use these a lot. The derivative of a function. You know, this derivative is defined with this limit. And the rest of chapter 3, we learn other rules and other ideas, and we kind of forget about the limit. We learn shortcuts, and some of them are long cuts actually, but we learn some shortcuts, and we don't do this limit process every time. We do here in section 3.1. But you know, if it's a limit, sometimes a limit does not exist, you know? And so if the limit does not exist, the derivative doesn't exist. And so there's places where the function is non-differentiable. So those are things to worry about. I think I'll address that in another video. The places where the derivative might not exist. The non-differentiable places of a function. Okay. All right, I got a couple of videos coming up with some examples of actually doing this, but you've done this in chapter 2. You just didn't know it was called the derivative. Maybe you didn't know it was the slope of the tangent line. This is a new big idea. So good luck. I hope you like it.